We are starting with magnetostatic in this lecture. The source of magnetostatic is DC current. Let me talk about the analogy with the electric field and magnetic field. So electric field intensity is measured in volt per meter, and magnetic field intensity is measured in ampere per meter. Magnetic electric flux density D, it is measured in coulomb per meter square, and magnetic flux density B, it is measured in Weber per meter square. D is equal to epsilon into E, and B is mu into H. Electric flux is measured as double integration d vector dot ds vector, and its unit is coulomb, and magnetic flux is measured as double integration b vector dot ds vector, and the unit is Weber. Now we come to the Biot-Savart law. It states that the differential magnetic field intensity dH produced at a point P by the differential current element IDL is proportional to the product IDL and sine of angle alpha between element and the line joining point P to the element, and it is inversely proportional to the square of the distance r between point P and the element. So mathematically mod of dH is proportional to IDL sine alpha, where IDL is the small current carrying element and alpha is the angle between line joining point P and the current carrying element. So mod of dH is proportional to IDL sine alpha, and mod of dH is inversely mod of dH is inversely proportional to 1 over r square. Okay, so mod of dH is proportional to IDL sine alpha over r square. So when we remove the proportionality, then constant is 1 over 4 pi. Then mod of dH is IDL sine alpha by 4 pi r square. This is the magnitude form of Biot-Savart law, and the vector form is IDL vector cross AR vector by 4 pi r square. This is the vector form, where AR vector is final minus initial by magnitude. Now there is one question that calculate magnetic field intensity due to infinite long current carrying wire. So let me derive this expression. There is infinite length current carrying wire in which DC current I is flowing, and we are taking a small current carrying element here, which is IDL vector, and IDL vector is I dz az vector. So the coordinates of this small current carrying element, it is 0, 5, z, and the point where we have to calculate the magnetic field, it is rho phi 0. So AR vector is rho minus 0 arrow, it is rho arrow, plus phi minus phi, it will cancel, plus 0 minus z az divided by under root of rho square plus z square. So according to Biot-Savart law, dH vector is IDL vector cross AR vector by 4 pi r square. So I dz az vector cross AR vector, it is final minus initial by magnitude. So it is rho arrow minus z az by under root of rho square plus z square by 4 pi rho square plus z square. So az cross arrow, it is a phi, and az cross az, it is 0. So dh vector, it is I dz by 4 pi rho square plus z square to the power of 3 by 2 and rho a phi. So total magnetic field H, it is integration of dh vector. So it is I dz into rho a phi by 4 pi rho square plus z square to the power of 3 by 2. So I upon 4 pi a phi, it is we will integrate it with the limit for the limit of minus infinity to plus infinity. So I by 4 pi a phi rho dz upon rho square plus z square to the power of 3 by 2. So z is rho tan theta. So dz is rho sec square theta d theta. Now we have to solve this integration. So when z is minus infinity, theta is minus of 90 degree. When z is plus infinity, theta is plus 90 degree. So we will just put here I by 4 pi a phi minus 90 to plus 90 and rho, and dz is rho sec square theta. So it is rho square sec square theta d theta upon rho square plus z square. Z square is rho square tan square theta. So this value is I by 4 pi a phi vector into 1 over rho minus 90 degree to plus 90 degree sec square theta by sec cube theta d theta. So it is 1 over sec theta and 1 over sec theta is cos theta. So I by 4 pi rho a phi vector minus 90 to plus 90, this is cos theta d theta. So I by 4 pi rho a phi, the integration of cos theta is sin theta. So it is from minus 90 degree to plus 90 degree. We will integrate. So this value is 2. So I by 2 pi rho a phi. So this is our required answer. So this is the magnetic field intensity due to the infinite line current. So there is one small question. An infinite wire is placed along z-axis. It carries current of 10 ampere in plus z direction. Calculate magnetic field intensity at point 3, 6, 12. So this question is given. So in the direction of z-axis, current I is given, and we have to calculate the magnetic field at 3, 6, 12. So on the z-axis, x and y are 0, and we will take z same as 12 because we have to calculate the perpendicular distance rho. So rho is under root of 3 square plus 6 square, it is under root of 9 plus 36. So rho is under root of 45. So it is h is I by 2 pi rho direction a phi. So it is 10 by 2 pi. Pi is 3.14 into rho. Rho is under root of 45 and a phi vector. So we can calculate this a phi vector in terms of Cartesian coordinate system. So it is ideal vector cross AR vector. So a phi vector, it is ideal vector, it is AZ vector cross AR vector. It is 3AX plus 6AY by under root of 9 plus 36. We will divide with the magnitude, and AZ cross AX is AY, and AZ cross AY it is minus of AX, so 3AY minus 6AX by root of 45. So H vector is, we will solve it, I by 2 pi rho and direction is a phi. So this is our answer, it is 0.23 and 3AY minus 6AX by root of 45. So this is our answer for magnetic field intensity. One more question. An infinite current carrying wire is placed along x-axis having current of 5 ampere in the plus x direction. Calculate magnetic field intensity at point 6 minus 2, 5. So current is flowing in the x-axis, and we have to calculate the magnetic field at 6 minus 2 5. So initial point will be 6 0 0, because on the x-axis y and z both are 0. So we will take 6 here because we have to calculate perpendicular distance. So rho, which is a perpendicular distance of this point and this point, so it is under root of 2 square plus 5 square, and it is under root of 29. So AR vector is minus of 2AY plus 5AZ by under root of 2 square plus 5 square. So the magnitude of H vector is I by 2 pi rho, and direction is A5. So 5 upon 2 into 3.14 into rho. Rho is under root of 29 and direction is A5. A5 is the direction of magnetic field vector H vector, which is equal to ideal vector cross AR vector. And ideal vector is AX vector because the current carrying element is placed in the X direction. And AR vector is minus of 2AY plus 5AZ by root of 29. So AX cross AY, it is AZ. So minus of 2AZ plus 5 AX cross AZ, it is minus of AY. So 5 into minus of AY by root of 29. So the value of magnetic field intensity, it is 0.14 into minus 2AZ minus 5AY by root of 29. So this is our answer. Next question is calculate magnetic field intensity due to finite length current carrying element. So this is given finite length current carrying element where height is varying from Z1 to Z2, and this is the point P where we have to calculate the magnetic field intensity. It is rho phi 0. So the value of AR vector, it is rho a rho minus z a z by under root of rho square plus z square. This is the final point, and here is the initial point 0 phi z. So 0 phi z1 and 0 phi z2, these are the two extreme points of the current carrying element. So dH vector is ideal vector cross AR vector by 4 pi r square. So I dz az vector by 4 pi rho square plus z square, and cross product with AR vector. AR vector is rho a rho minus z az by under root of rho square plus z square. When we cross product az with arrow, it is az cross arrow is a5 and az cross az is 0. So dH vector is I dz rho a5 by 4 pi rho square plus z square to the power of 3 by 2. Total magnetic field H vector, it is integration of dH vector. So H vector is I by 4 pi a5 vector integration z1 to z2 rho dz upon rho square plus z square to the power of 3 by 2. So first to solve it, we will put z is equal to rho tan alpha. So dz is rho sec square alpha d alpha. When z is equal to z1, alpha is alpha 1. When z is equal to z2, then alpha is alpha 2. So H vector, it is I by 4 pi a5 vector alpha 1 to alpha 2 rho into rho sec square alpha d alpha by rho square plus rho square tan square alpha to the power of 3 by 2. So I by 4 pi rho, direction is a5, and limit alpha 1 to alpha 2 sec square alpha upon 1 plus tan square alpha is sec square alpha, and sec square alpha to the power of 3 by 2, so it will be sec cube alpha. So I by 4 pi rho a5 vector and alpha 1 to alpha 2, it is cos alpha d alpha. Then I by 4 pi rho sin alpha 2 minus sin alpha 1, and direction is a5. So this is the magnetic field intensity due to finite length current carrying element. So we have to solve, suppose this question, that calculate magnetic field intensity due to finite length wire of length A placed along y-axis at point A by 2, comma A by 2, and carries current I in y direction. So this is the finite length current carrying element, and we have to calculate the magnetic field intensity at point A, which is A by 2, comma A by 2. So let me join these two ends, and this angle is minus of 45 degree and this angle is plus 45 degree. So alpha 1 is minus 45 and alpha 2 is plus 45. So H vector, it is I by 4 pi rho sin alpha 2 minus sin alpha 1 A phi vector. So I by 4 pi into A by 2 sin of 45 minus sin of minus 45 A phi vector. So I by 2 pi A, 1 by root 2 plus 1 by root 2 A phi. So this answer is I by 2 pi A, 2 by root 2 A phi. So this answer is I by root 2 pi A, direction is A phi vector. We can also calculate the A phi vector, ideal vector cross AY vector. Ideal vector is AY vector and AR vector it is AX. So AY cross AX it is minus of AZ. So H vector it is I by root 2 pi A, direction is minus of AZ. Now next question is given a square loop having side length of A, find the magnetic field intensity at center. So this is the square loop in which current I is flowing in the clockwise direction. So this is the case where the magnetic field intensity will be 4 times of the previous one, because this is the finite length current carrying element which is from this point to this point, and this is again a finite length current carrying element. In the same direction magnetic field will appear. This is also the finite length current carrying element, and this is again the finite length current carrying element. So the final answer is 4 times the previous. So the final answer is I upon root 2 pi A, direction is minus of AZ into 4. So this answer is 4I upon root 2 pi A minus of AZ vector. So this is our answer for it. Now the next question is, a circular ring of radius A carries current I in a phi direction, which is anti-clockwise direction. Calculate magnetic field intensity at point P at height h above from the center of the ring. So the question is, a ring is given, a circular ring is given, which is carrying current I in the anti-clockwise direction, and we will take one current carrying element here, which is ideal vector, and ideal vector is IA d phi A phi vector. The coordinate of this point is A comma phi comma 0. This is our initial point, and we have to calculate magnetic field at this point. So according to Biot law, a DH vector is ideal vector cross AR vector by 4 pi R square. So ideal vector is IA d phi A phi vector cross AR vector. So Biot law, it states that the differential magnetic field intensity dH produced at a point P by the differential current element ideal is proportional to the product ideal and sine of angle alpha between the element and the line joining point P to the element, and it is inversely proportional to the square of the distance r between point P and the element. So mathematically we write Biot law as mod of dH, it is proportional to ideal sine alpha, and mod of dH, it is inversely proportional to distance square. So it is mod of dH it is inversely proportional to 1 over r square. So this is differential current carrying element, it is ideal, and this is angle alpha. So mod of dH is proportional to ideal sine alpha by r square, and when we remove differentiation, so mod of dH, it is ideal sine alpha by 4 pi r square, and this is the magnitude form. When we talk about the vector form, then ideal vector cross AR vector by 4 pi r square. This is the vector form where AR vector is final minus initial by magnitude. So let me calculate magnetic field intensity due to infinite long current carrying wire. Suppose there is an infinite long current carrying wire placed along z axis. So the initial point here is 0, 5, z. We are taking a small current carrying section here, ideal vector, which is I dz az vector, and this is the point P where we have to calculate the magnetic field. It is rho phi 0. So AR vector is rho arrow minus z az by under root of rho square plus z square. So according to Biot law, dH vector is ideal vector cross AR vector by 4 pi r square. So ideal vector is I dz az vector cross AR vector. It is rho arrow minus z az by under root of rho square plus z square divided by 4 pi rho square plus z square. When we cross multiply, cross product it, then az cross arrow it is fi, and az cross az is 0. So dH vector is here I dz upon 4 pi rho square plus z square to the power of 3 by 2 and rho fi. So total magnetic field H vector, it is integration of dH vector which is equal to I dz into rho fi by 4 pi rho square plus z square to the power of 3 by 2. So I by 4 pi fi it is rho dz upon rho square plus z square to the power of 3 by 2. So we have to solve this integration minus infinity to infinity rho dz upon rho square plus z square to the power of 3 by 2. So we are putting here z is equal to rho tan theta. So dz is rho sec square theta d theta. When z is minus infinity, then theta is minus 90 degree. When z is plus infinity, then theta is plus 90 degree. Then total magnetic field H vector, it is I by 4 pi a phi minus 90 to plus 90 rho square sec square theta upon rho square plus rho square tan square theta to the power of 3 by 2. So I by 4 pi a phi, we will take common, rho square will take common. So rho cube will come because rho square to the power of 3 by 2. So rho square and rho cube will cancel, so 1 over rho will present here. So it is minus 90 to plus 90 sec square theta by sec cube theta. So this will cancel each other and 1 over sec theta will remain. 1 over sec theta is cos theta. So the integration of cos theta, it is sine theta. So it is I by 4 pi rho sine theta minus 92 plus 90. So when we solve it, sine 90 minus sine of minus 90, it is 2. So the answer is I by 2 pi rho, direction is A5. So this is the magnetic field intensity due to infinite length current carrying wire. Now the question is, an infinite wire is placed along z axis and it carries current of 10 ampere in plus z direction. Calculate magnetic field intensity at point 3, 6, 12. So the current carrying wire is placed along z axis and it is carrying current I, and at point 3, 6, 12 we have to calculate the magnetic field. So we have to take one initial point here. On the z axis, 2 points are fixed, x and y, and x and y are 0, 0. But third point will take only 12. So that we can calculate the perpendicular distance. So the value of rho, it is under root of 3 square plus 6 square, and this comes as under root of 9 plus 36. So rho is under root of 45. So h vector, it is I upon 2 pi rho a phi. So I upon 2 pi rho a phi, it is I is 10, 10 upon 2 pi, pi is 3.14, and rho is under root of 45, and direction is a phi. We can calculate direction a phi in the Cartesian coordinate system. A phi is ideal vector cross AR vector. As ideal vector, current carrying wire is placed along z axis. So a phi vector is AZ cross AR vector is 3ax plus 6ay by under root of 9 plus 36. So a phi vector is AZ cross AX, it is 3ay minus 6ax by root of 45. So we will solve it and we will get our answer. H vector is 0.23, 3ay minus 6ax by root 45. So this is our desired answer. And the next question is, an infinite current carrying wire is placed along x-axis having current of 5 ampere in the positive x direction. Calculate magnetic field intensity at point 6 minus 2, 5. So current carrying wire is placed along x-axis and we have to calculate the magnetic field at 6 minus 2, 5. So the 2 points on the x-axis are fixed, that is y and z, they are 0, 0. So third point we will take 6 only because we have to calculate the perpendicular distance rho. So the value of rho here is under root of 2 square plus 5 square. So rho is under root of 29 and AR vector is minus of 2ay plus 5az by under root of 2 square plus 5 square. So h vector, it is I upon 2 pi rho, direction is a5. So 5 upon 2 pi is 3.14 into rho, rho is under root of 29 in a5 direction, a5 vector. So a5 vector is direction of h vector, it is ideal vector cross AR vector. Ideal vector is AX vector and cross AR vector is minus of 2ay plus 5az by under root of 29. So AX cross AY, it is AZ. So minus of 2az plus 5 minus of AY by root of 29. So H vector is 0.14 minus of 2az minus of 5ay by under root of 29. Now the next question is calculate magnetic field intensity due to finite length current carrying element. Now this is the figure where finite length current carrying element is given from Z1 to Z2, and at point P we have to calculate the magnetic field. So the coordinates of the lower point is 0, 5, Z1 and the coordinates of upper point is 0, 5, Z2. So dH vector is ideal vector cross AR vector by 4 pi R square, which is equal to I dz dz vector cross AR vector. AR vector is rho minus 0 arrow plus 5 minus 5 will cancel plus 0 minus Z divided by under root of rho square plus Z square. So I dz rho fi by 4 pi rho square plus Z square to the power of 3 by 2. Total magnetic field H vector, it is integration of dH vector so it is I by 4 pi A5, and we will take the limits from Z1 to Z2. So it is rho dz upon rho square plus Z square to the power of 3 by 2. So we'll put here Z is equal to rho tan alpha and dz is equal to rho sec square alpha d alpha. So dz is rho sec square alpha d alpha. When z is equal to z1, then alpha is equal to alpha 1, and when z is equal to z2, alpha is equal to alpha 2. So it is I by 4 pi fi alpha 1 to alpha 2 rho into rho sec square alpha d alpha upon rho square plus rho square tan square alpha is to the power of 3 by 2. So I by 4 pi rho a5 alpha 1 to alpha 2 sec square alpha by sec cube alpha. So I by 4 pi rho a5 alpha 1 to alpha 2 1 upon sec alpha, it is cos alpha. So the integration of cos alpha is sine. So I upon 4 pi rho sine alpha 2 minus sine alpha 1 a5 vector. So this is our answer. So H vector, it is I by 4 pi rho sine alpha 2 minus sine alpha 1 a5 vector. Now we have to calculate the magnetic field intensity due to finite length wire of length A placed along y-axis at point A by 2, A by 2. So this wire is placed along y-axis and carries current I in the y direction. So this is the final point where we have to calculate the magnetic field at point A by 2, A by 2. So the initial point obviously will be 0, A by 2. Lower limit is 0, 0 and upper limit is 0, A. So the value of alpha 1 is minus 45 and value of alpha 2 is plus 45. So H vector it is I by 4 pi rho sin alpha 2 minus sin alpha 1 a5 vector. So H vector, it is I by 4 pi a by 2 sin 45 minus sin of minus 45 a5 vector. So I by 2 pi a 1 by root 2 plus 1 by root 2 a5 vector. So I by 2 pi a into 2 by root 2 a5 vector. So it is I by root 2 pi a a5 vector. A5 vector is ideal vector cross AR vector So it is ay cross ax, which is minus of az. Biot law, it states that total magnetic field intensity dH produced at a point P by the differential current element ideal is proportional to the product ideal and sine of angle alpha between the element and the line joining point P to the element, and it is inversely proportional to the square of distance r between point P and element. So mathematically, we write here, if this is the angle alpha between the small section ideal and point P, so mod of dH is proportional to ideal sine alpha, and mod of dH is proportional to 1 over r square. So mod of dH is proportional to ideal sine alpha by r square. So mod of dH, when we remove the proportionality here, then constant appears. So mod of dH, it is ideal sine alpha by 4 pi r square. This is the magnitude form. So dH vector is ideal vector cross AR vector by 4 pi r square. AR vector is final minus initial by magnitude. Suppose we have to calculate the magnetic field intensity due to infinite length current carrying wire. So the infinite length current carrying wire is placed along z-axis, and we have taken a small section on this wire which is ideal vector, and ideal vector is I dz az vector. The coordinates of this point is 0, phi, z, and we have to calculate the magnetic field at rho, phi, 0. So the distance between these 2 points are under root of rho square plus z square, and AR vector is rho arrow minus z az by under root of rho square plus z square. According to Biot law, dH vector is ideal vector cross AR vector by 4 pi r square. So I dz az vector cross rho arrow minus z az by under root of rho square plus z square divided by 4 pi rho square plus z square. So I dz upon 4 pi rho square plus z square to the power of 3 by 2. It is AZ cross arrow. AZ cross arrow is A phi, so it is rho A phi. So total magnetic field is the integration of this magnetic field. So it is I dz upon 4 pi rho square plus z square to the power of 3 by 2 rho A phi. So I by 4 pi and A phi vector and integration rho dz upon rho square plus z square to the power of 3 by 2. Limit is minus infinity to plus infinity. We put z is equal to rho tan theta. Hence dz is equal to rho sec square theta d theta. When z is minus of infinity, then theta is minus of 90 degree. When z is plus infinity, theta is plus 90 degree. So this answer comes as I by 4 pi A phi vector minus 90 to plus 90 rho square sec square theta upon rho square plus rho square tan square theta to the power of 3 by 2. So I by 4 pi A phi vector into 1 over rho minus 90 to plus 90 sec square theta upon sec cube theta. So it is 1 over sec theta, which is equal to cos theta. So I by 4 pi rho A phi vector and integration of cos theta, it is sin theta minus 90 to plus 90. So H vector is I by 4 pi rho A phi vector. So question is, an infinite wire is placed along z-axis and it carries current of 10 ampere in the plus z direction. Then calculate magnetic field intensity at point 3, 6, 12. So we have to calculate the magnetic field intensity at point 3, 6, 12, where this is the initial point 0, 0, 12. So the value of rho, it is under root of 3 square plus 6 square. Rho is under root of 45. So the value of H vector, it is I by 2 pi rho, direction is A phi. So I by 2 pi rho, I is 10, 2 pi, pi is 3.14, rho is under root of 45, A phi. A phi vector we can also calculate in Cartesian coordinate system. It is ideal vector cross AR vector. So it is AZ vector cross AR vector is 3AX plus 6AY by root of 9 plus 36. So A phi vector is 3AY minus 6AX by root of 45. So H vector, it is 0.23 into 3AY minus 6AX by root 45. So this is our answer for this question. A infinite current carrying wire is placed along x-axis having current of 5 ampere in the x direction. Calculate magnetic field intensity at point 6 minus 25. So a current carrying wire is placed along x-axis where we have to calculate the magnetic field intensity at 6 minus 25. So initial point is 600 and the final point is 6 minus 25. The distance between these 2 points are under root of 2 square plus 5 square. So the value of rho, it is under root of 29. So h vector, it is I by 2 pi rho a5 vector. So it is 5 by 2 pi. Pi is 3.14 and rho is under root of 29 a5 vector. A5 vector is direction of h, and h vector direction can be calculated as ideal vector cross AR vector. So it is calculated as ideal vector, it is AX vector cross product with minus 2AY plus 5AZ by root of 29. So when we solve it, AX cross AY, it is AZ, so minus 2AZ plus AX cross AZ is minus of AY, so minus 2AZ minus 5AY by root of 29. So H vector, it is 0.14 minus 2AZ minus 5AY by root 29. So this is our desired answer.